Do you guys have any question before we go? No? Okay. Let me briefly let me briefly review what we talked in the last class. So we talked about the fact analysis, right? We overviewed the fact analysis, and we talked about the principal axis factoring. So first, so fact analysis is a linear combination of the latent variable, right? So fact analysis is a linear combination of a latent variable, but principal axis, no, I'm sorry, principal component analysis, PCA, is a linear combination of observed variable, right? So the latent factor, the F, the latent factor is, that is underlying constructors or latent variables in FA. And also generally the number of factors is smaller than number of variables. So theoretically, we can have the same number of factors, but so our goal is to reduce the dimensionality. So we try to reduce the dimension based on the set of items, set of predictors or variables. So fact analysis and principal component analysis, the both are aimed to reduce the dimension. We try to find the simplest structure in a set of variables. So like I said, principal component is a linear combination of original variable, right? But the fact analysis is a linear combination of factors. So principal component analysis to use reduced correlation metrics. No, I'm sorry. So original correlation metrics, right? So the diagonals, the commonality is always one. So that means the total variance is equal to the common variance. But fact analysis uses reduced correlation metrics. So it only use commonality except for the residual variance. So we'll more talk about that. So this is the formula, the basic formula of orthogonal factor analytic models. So mu, this is intercept. This is very similar to the regression model, right? So this is the intercept, and then these are factor loadings, and these are factors. In this case, we have multiple factors, factor 1, factor 2, and factor m. And these are the residual variance. Okay, this is error term. Okay, so the coefficient loading, this is called the factor loadings. So how can we interpret the loadings in the standardized solution? So like if you use the correlation matrix, factor loading is a correlation between the predictor and the factor. Okay, so this is a reduced form, right? So if we get, if we simplify these formulas, that we can get this formula, right? So mu minus, actually this is mu plus lambda f plus error, right? So this is, what is it? This is mean, right? This is intercept. And this is factor loading matrix. This is a factor loading matrix. So this is a factor loading matrix right here. And the F is our factor. And then this is our error, residual error, right? So if you use correlation matrix, that means you're going to standardize it, right? So if you standardize it, so this mu, this mean will be 0, right? So if you run a standardized solution or correlate, if you use correlation metrics, generally you will not get the mean. Okay, so it will be simplified like loading f plus e. Okay. Right. So the expected value of each factor is 0, right? So that means the mean of each factor score is 0. Okay, and then this is the This is an assumption of orthogonal factor analytic model. Okay, so covariance of factor scores is identical. So that means 1, for example, this F1, F2, F3, F4, they are all orthogonal. Okay, they are not related to each other. This is the assumption of the orthogonal factor analytic model. Okay, so covariance of a factor score is also noted by this psi. Is it psi? Is it Jai? I'm not sure. So it's this notation. Okay, so we'll see later. And then also the expected value of residual is 0. And like I said, this is the error variance, residual variance, right? So residual variance, so this is a variance of a residual factor. So this is residual variance. And also our factor score is uncorrelated with error. So there is 0. Okay. So assumption made above is the simple explanation. This is the variance of our observed variable is sum of factor loadings plus error variance. The sum of factor loading, this part is what? This is communality. Okay, so it's like R square in the regression model. And then this is error variance. Okay. And then covariance metrics of our observed variable. So like I said, the y equals f plus this one, right? Your mean is 0 in this case. So covariance of this formula can be rewritten like this. So because the f and error is uncorrelated each other, so we can rewrite this one. So covariance, factor gamma and factor loading plus error is equal to, this will be like this. So covariance of error variance is like this. So lambda and covariance of f is I, and then lambda transpose and sigma. So this is identical matrix. So this is a final form. So our covariance matrix can be expressed by the matrix form. Okay. So this is very important because look at this. Here, this is the factor loading, and this is transpose of our factor loading, and this is covariance of our factor scores, right? So if this covariance of a factor score is identical, that is 0, 0, 1, 0, 0, 0, 1, like this, right? But that means our factors are orthogonal, right? Because there is no correlation. But if we allow the covariance between factors, so for example, 0.3, 0.4, 0.3, what will happen to here? If you multiply the vector to matrix, that means that is a linear transformation of your factor, right? So if we allow covariance in this factor covariance matrix, that means rotation. Okay, so we will allow rotation in this case. This is formula form. So this is our covariance matrix, right? This is covariance matrix. So this is variance, and these are all the covariance between 1 and 2. Okay, so this is factor loading matrix times transpose of a factor loading, and this is a psi. So if you multiply this one, so that means 1 times 1 is this one, and 1 times 1 is covariance. So we can get this matrix, okay? So diagonal is all the variance, and the off diagonal is all the covariance. And then if you add this psi, so that is lambda square, because this part is added by this part. If you add these two, we will get this one. If you add these two, we'll get this one, right? So, oh, yeah. So this part is our variance. This is our total variance. Okay, so total variance is what? This is commonality plus error. Okay, this is commonality of error. This commonality plus error. Okay, does that make sense? Question? No. So the covariance between observed the variable and factor is the factor loading. Like I said, the factor loading is covariance or correlation between your variable and factor scores. Okay, and that can be written like the loading metrics, and also lambda square, sum of lambda square. If you sum all the lambda square, so factor loading, that is commonality. And then this is specific variable, a variance, that is error variance. If you sum it, that is 1. Okay, so this relationship is right here. Sum of squared loading, that is commonality, and psi 1 is residual. So this is 1, 1, 1. Okay. Right. So any question before we move? We talked about this in the last class. And then let me review PCA algorithms. The PCA, so to do the PCA, we do the mean centering and standardize and normalize. So we use the correlation matrix and get the eigenvalue and eigenvector from the correlation matrix. And we order eigenvalues and eigenvectors, right? And then we can compute the Z using the eigenvector. So these values are all the eigenvectors, right? This is eigenvector of the largest eigenvalue. This is eigenvector for the second largest eigenvalue, right? So this is the PCA. So we start from the PCA to talk about the principal factor axis factoring. So let's say we have reading score and writing score, and we have 10 observations. And first, we can compute the correlation using this data. That is right here. So this is reading, this is writing, and get the eigenvector. So first eigenvector and second eigenvector, and then we can get the eigenvalue and eigenvector. Okay, using this information. This is the PCA, right? So this is the PCA. So PCA used full correlation metrics, but the PAF, this is principal axis factoring. This is EFA, the estimation method. So it use R squares for instead of the 1 in the diagonal, right? So the reading equals the writing, and we can compute the R square, and writing equals to reading and equals R square. So we can get R square and R square. And we use this R square instead of 1. Okay, we replace this R square by instead of 1 in the diagonal. So then we use this correlation matrix as the initial correlation matrix to estimate the principal, to estimate the loading and residuals. Okay. So here are, so principal axis factoring and the PAF and maximum likelihood estimation. These two methods are most commonly used. Okay. And principal axis factoring use correlation and covariance. Initial values and iteration is important. So this is default in SPSS and Stata or R. This is very popular method. And maximum likelihood assumption, maximum likelihood estimation assumes observation follows the multivariate normal. Okay, and then we try to find maximum likelihood value of loading matrix and residual matrix, okay, through the iteration process. And unweighted least squares, the generalized least square, and many other the estimation methods are possible, but generally we use these two methods. So PAF, so this is our original matrix, but we replaced our diagonal by communality, right? And then this is our initial, the updated communality. Okay, so this is iteration step 1. So we are using new communality. And then get the, using from this correlation table matrix, that we compute eigenvalue and eigenvector. And then using eigenvector and eigenvalue, we can compute the factor loading. So factor loading is eigenvector times square root of eigenvalue. Okay, that is the standard deviation of eigenvector. Eigenvalue is the factor loading. Okay, and then 0.707 times point square root to 1.94 is 0.98. This is factor loading. Okay, this is the factor loading. And then if we do this same, and it is 0. Okay. And then do you remember the first factor loading square plus the second factor loading square is what? This is communality, right? This is communality. So our communality is 0.98 square plus 0 square. That is communality, updated communality. And then this is square and square. If you add them, 0.97, that is updated communality. Okay. So this is our original communality, and this is our updated communality, right? And then now we can get the difference between these two. And then square it, right? And add difference between these two and square it. And that value is 0.00196. And but our criterion is 0.0001, okay? So we want this value is less than this criterion, but this value is still greater than our communality criterion. So we'll do one more iteration step. Okay, so and then our communality is updated now using 0.97, 0.97. And do it again. Compute eigenvalue and eigenvector from this correlation and update it. And then compute factor loadings and get the communality. Okay. And then update our communality again. and then compute the difference, square it, difference, square it. That is 0.00049. This is still greater than our criterion. So we repeat this process again. One more. So now update our commonality here and using compute eigenvalue, eigenvector, compute factor loading. This should be 5. And communality, and update again. And get the difference and square it. Difference, this one minus this one, and square it, plus this one minus this one, square it. And we get this one. This is still greater than our criterion. And one more time, almost there. And our commonality is updated again. Compute eigenvalue, eigenvector, and factor loading, and get the commonality, right? And then this is our previous commonality, updated commonality, and then get the difference. So this value is still greater than our criterion. So we'll repeat one more time. This is less time. So, and then now, this is updated commonality. So we compute eigenvalue, eigenvector, and factor loading, commonality, and compare. And get the difference and square it. And then now this value is less than our criterion. Okay, and then stop. So this is our final solution. Okay, so right here. Okay, so let me interpret our final solution. So this is our final solution. This is factor 1 and factor 2, and reading and writing. Okay. So factor 1, the reading is, the correlation between reading and factor 1 is 0.989. It's really, really high, right? The correlation between reading and factor 2 is 0. So factor 2 doesn't contribute anything to our total variance. What about writing? Writing is 0.98. So the correlation between writing and factor 1 is 0.98, and the factor 2 is 0, right? So, okay, maybe we can pick one factor solution, okay? And then your job is to name the factor 1. So how do you identify, how do you name the factor 1 in this case? The reading and writing, maybe it will be language ability or something like that, right? Okay, so here are some commonality, the changes. So this is our initial commonality, right? As iteration increase, our commonality increases, right? So it was 0.96, but our final commonality was 0.9792. As iteration increases, the commonality increases. So iteration increases, so eigenvalue also increases. Because commonality increases, so eigenvalue definitely increases, right? Because eigenvalue is from the correlation matrix. Okay. So, okay, and then this is our final matrix, like I said. So 0.99, that is a factor loading of our, this is factor loading. Okay, factor loading is a correlation between factors and the values. Okay, and the commonality is this one square, this one is commonality. So let's say this is lambda 1 square lambda 2 equals 0.979. So how can we interpret this one? Anybody? How do you interpret the commonality? Any idea? No? So that means 92%, 97.9% of total variance in reading is explained by these two factors. Okay, so in this case, factor 2 is 0, so we ignore this one. So that means factor 1, single factor explains reading almost 97%. Okay, what if this case? Let's think about, let's say this is a 0.7 and this is a 0.3. Okay, and I just made it up, okay? And then our commonality is a 0.8. No, what is it? 0.49 plus 0.09 is, I just square it, right? So that is 0.58. Okay, how can we interpret this? If the commonality is 0.58.
I would say 58% of the variance in reading could be explained by factor 1 and factor 2.
Yes, factor 1 and factor 2. In this case, the factor 2 had some factor loadings, right? So two factors contributes to the commonality of the variable. Okay.
So how do we get the total commonality here? Is that average of those commonalities?
The total commonality? Yeah, average.
Okay.
Yeah. So your RL output will provide you. This is Princess axis factoring. So when you run Princess axis factoring, sometimes the convergence fails. Okay, because I think the default is 25 iteration. So if your data, the covariance matrix is complicated, in that case, 25 iteration is not enough to get the stable result, okay? So in that case, you need to increase the number of iteration from 25 to 50 or 100, okay? So it will go, it will repeat this process 100 times, and then it will stop, okay? And this is PAF, and then this is maximum likelihood estimation. So we learned about maximum likelihood estimation, right? This is multivariate normality assumption for the multi likelihood ratio, right? So this is a multivariate distribution. And then this case, we want to estimate, we want to get the maximum likelihood value of mean and covariance matrix, right? So we compute the likelihood value based on the data set, okay? The given data set, we compute our likelihood value, okay? All different likelihood value and find maximum likelihood value. That is our estimated parameter, right? This is what we talked. So maximum likelihood estimation for exploratory factor analysis, just still same. Instead of using mu and sigma, we need to estimate loading and error variance, right? Based on our data. So we will compute all possible likelihood values of loading and residuals based on our data, and then find maximum likelihood. Okay. So that is maximum likelihood estimation for EFA. Okay. But maximum likelihood estimations are found through the iterative numerical methods. So first, okay, so the first iteration, we found the maximum likelihood values like the 0.003, and the second iteration, maximum likelihood value 0.013, and third iteration 0.023, and we repeat this process. And if this increasement is not significant, okay, if this increasement of maximum likelihood value is insignificant, then stop. Okay, so this is iterative numerical method. And then final solution is loading, estimated loading, and estimated residual variance. Okay, so PAF and likelihood estimation, they have very different, they take very different approach, but the results are pretty similar, is very similar. Okay. So, and in our package, we, the FactAnal package, and FA package, actually FA function is from Psych package. Okay. So these two packages are the very commonly used, but FactAnal, this package only use ML estimation. But FA package use multiple estimation method. It has some options than ML, PAF, and we'll see later. Okay. Right. So, and then how can we choose the number of factors? Right. So, you know, the 70% or 80%, we want to retain 70% or 80% of the total variance. Okay. So if your 3 factors explain the 70%, maybe you can stop there. Or 4 factors explain 80%. So there is no strict rule of thumb here, but generally we say the 70% or 80%. And also you can retain the factors that having the eigenvalue greater than 1. It's the same for the PCA. And you can also use a script plot and find the elbow point, right? And then you can stop it. And then MLE estimation, so provides likelihood ratio test. If you use FactAnal package, so it provides this information. Okay, so null hypothesis is M factors are sufficient. And alternative hypothesis, more common factors are needed. So based on some metrics formulations that they tested some likelihood ratio test. Okay, so if the p-value is less than 0.05, that means we reject null hypothesis. That means, okay, we need more factors. Okay, so FactAnal package provides this information. Okay, but I think that generally we use these 3 criteria. So I don't see any research used this approach. Okay, so when you decide your number of factors, you need to look at the total variance, eigenvalue, and script plot. Okay, so this is rotation. So, I mean, you don't have to memorize anything from here, but I will just explain it, okay? So what is this? This is our covariance matrix, right? Covariance matrix that can be decomposed into 2 sets of matrix form, loading and loading transform, transpose loading plus error, right? And then we can multiply T times T transpose, the T is orthogonal matrix here. Okay. So T times T transpose is 1 at the identical matrix. So for example, 3 times 4 equals 1. But 3 times 1 times 4 is still, I'm sorry, 12 and 12, right? So here, 1 is right here. And then we can rewrite like A lambda loading times orthogonal plus loading times orthogonal and transpose plus residual variance. Because AB transpose is B transpose times A transpose. We learned that. So this relationship is like this. Let's say lambda times orthogonal is new lambda. It's right here. And then new lambda transpose and Y. So this relationship can be rewritten this relationship, right? So look at this. This is our factor. This is loading, and this is orthogonal, the matrix. If you multiply some new matrix to your vector, it will do the linear transformation. So that is rotation. Okay, so let me say differently. So this is our covariance. This is our covariance matrix, right? And lambda matrix times lambda transpose plus residual variance. What is this? This is covariance of a factor loading, right? So if we allow the covariance in the covariances matrix, for example, like the 1.5, 0.5, 1.4, 1, like this, so we allow some covary in this matrix, right? So that means your factors will be rotated. Okay. Does that make sense? Questions here? So, okay, because the fact rotation is important. What if this factor correlation is 1, 0, 0, 1, 0, and 0? What happens? What will happen to our factors? What is the relationship between factors?
Orthogonal.
Orthogonal, right? Because we don't allow covariation between different factors. But if we allow, this is a very restricted format, but if we, allows the covariance in the covariance matrix of a factor scores, so it will rotate, okay? So we talked about in the first and second class, if you multiply vector and matrix, it will be the linear transformation, right? So original vector looks like this, but if you multiply some vector and matrix, you will have a new vectors. Okay, so we have two different types of orthogonal rotation. First one is orthogonal rotation. Orthogonal rotation preserves 90 degree. Okay, it keeps perpendicular between two factors or three factors, four factors. Okay, but oblique rotation so allows the factors to be correlated each other. So in this case, our sigma, lambda, psi, lambda plus y. So in this case, we have covariance of the covariance matrix of factor score covariance is not 0 in that case, but this case will be 0. And the oblimin and Promax is the most commonly used oblique rotation method. So look at this. Let's say we have a two-factor solution. So this is a factor 1 and this is a factor 2. Okay. And then this is our variables. Okay. This is our variables right here. And then maybe we can identify these variable as factor 2 because they are close to the factor 2, this factor, right? And then these are pretty close to this factor. But improve the interpretation, we can rotate our factor. So if we rotate our factor like this, this is the factor, but we rotate this much. And if we rotate x-axis to this much, and then this is new factor. This is a factor 1, and this is a factor 2. Okay. So factor 1, new factor 1 explains our data really well in this case. Right? But what about this case? We can still see some deviance, right? They are pretty close to factor new factor 2, but they're still, you know, a little bit far from the factor 2 in this case. But orthogonal rotation always keeps 90 degree. Okay. But the oblique rotation, it allows less than 90 degree. Okay. So we rotate this much. Maybe we can rotate more like this much. And we rotate this much. So this new factor 1 perfectly explains these variables. And rotated factor 2 explains this variable very well. Okay. It will improve interpretability of your factor solution. Okay. So which rotation method we should use? So orthogonal rotation and oblique rotation. So, you know, when factors are theoretically uncorrelated, in that case, you can use orthogonal rotation, which is called the Varimax approach. But when factors are theoretically correlated, so we use oblique rotation, oblique rotation method. Okay, but this is a more realistic case, right? Because in many cases, factors are related somewhat, right? So we use oblique rotation method. And the factor scores in MLE, do you remember we computed principal component scores in PCA? It's the same here. Okay, we can also compute the factor scores from the equation. Okay, so for example, y equals 1.4 F1 plus 2.3, let's say, y equals 0.4 F1 plus the 0.9 F2 plus the 0.6 F3. So this is the factor loadings, right? This is the factor loading. And then we estimated, we will estimate these factor scores. These factor scores using some advanced method. Okay, because getting factor scores in factor analysis is not simple as in the PCA. So the FA, that the package allows you to use many different approach. The first one is a regression approach, and third one approach, Ten-Burge and Anderson, Bartlett. So we will use the regression in the R expression, R demonstration. Okay. So F1, F2, F3. Let's say we computed 1.5, 0.2, minus 1.3. Okay. So first, an observation 1. Okay. His factor scores. First factor score is 1.5. And second factor score is 0.2. And third factor score is negative 1.3. So that means he has very high level of latent traits in the first factor. Okay. And he has a low level of latent trait for the third factor. Okay. Let me say differently. We'll see the factor score later. So let's say this, the first factor is openness. Second factor is conscientiousness. And third factor is extrovertness. Okay. And we computed the factor scores of first observations. And his factor score for openness is a positive 1.5. So that means his latent trait level of openness is very high. And negative 1.3 is his latent trait of extroversion is low. Okay. Mean is, expected value of F is 0. That means this factor score, mean of a factor score is 0. So you can interpret the factor score as a Z score. Okay. Right. So any questions before we move on to the R example?
One question about the orthogonal rotation and the EFA we learned last class. Are they the same thing here?
The which one?
The orthogonal rotation and the EFA we talked about last class.
Yeah.
So they are the same thing actually.
Yeah.
Okay.
Mm-hmm. Okay, so here is an example. So in this example, I will show you some items. Okay, let's say we have the 12-item scale, achievement goal scale, the 12 items. Okay, and then these 12 items were developed based on 4 different theoretical factors. Okay, mastery approach, mastery avoidant, performance approach, and performance avoidant. Let's say we have 12 items. These are 12 items. The first item, let's look at this. First item is my goal is to completely master the mastery presented in my class. So this is a mastery approach. This item was written to measure mastery approach. The second item, I want to avoid learning less than it is possible to learn. So this item was written to measure mastery avoidant. Okay. So let's say we have 12 items. The 12 items were written to measure the 4 different constructs. Okay. So, but these 2 constructs are mastery related construct, and these 2 constructs are performance related constructs. Okay. So our question is, by applying the factor analysis, following issues shall be resolved. First, we can decide the number of factors to be retained. Okay. So we have 12 items. We want to reduce the dimensionality. So how many factors will be possible is ideal, right? So what would be the total variance explained by these factors? And the second question is, we can identify the variable in each factor retained in the final solution on the basis of factor loading. Which items are loaded on belongs to which factor? Okay. So third, and then based on these results, we can give names. to each factor retained on the basis of the nature of variables included in it. Right. So you understand the questions? Okay, now let me go back to my slide. I'll. Okay, so to run first, we're gonna use FA function. Okay, so to run FA function, so psych package includes FA function. So you need to install the psych package first. I already installed it and loaded, and the core plot. This allows us to evaluate the correlation matrix plot. Guess I wrote it, and GPA rotation. This allows us to use some rotation method. So allow it, and then I'm gonna import my data set. What happened? Session, maybe multivariate, vector analysis. Okay, that will be fine. Okay, I load it, and then let's view our items. Okay, we have A1 through A12. We have 12 items, 7 Likert scale. Okay, and then how many? The 430. Okay, so let me close it. And then first, I want to check the correlation. Okay, because if you do not have strong correlation among your variables, there is no need to run the EFA or PCA, right? So I will run the correlation first. So this is a correlation matrix, but it's pretty hard to read it. So that's why I plot the correlation, core plot. So this is a correlation plot, correlation matrix. And then you can add in the core plot function. And this is order, these are all the options. Okay, so and then I run it. Okay, now you can see, right? So we have so all the positive relationships. So we can see a very clear patterns that these items are correlated very strongly each other, right? And these items are strongly correlated. These items are strongly correlated, right? You can see some general patterns here, right? Okay, now it's good. And then we're gonna conduct a Barrett test and KMO test to evaluate the suitability of a factor analysis. Okay, so the core test.Barrett, and this is our data set, and diagonal equals true. If you run it, it will give you some Barrett test results here. And the KMO test is right here. This is KMO. So let me explain the result using my slide. So this is a Barrett test. So Barrett test is a hypothesis testing. So our null hypothesis is identity matrix 1, 1, 1, and 0, 0, 0. Okay. So this is our null hypothesis. That means our null hypothesis is there is no relationship among variables. Okay. So if you reject this null hypothesis, that means there is statistically significant relationships among our variables, right? So this is degrees of freedom, and this is the p-value, the 0, less than 0.05. That's a good sign. That means we reject our null hypothesis. So that means, okay, there is a statistically significant relationships among variables. That is a Barrett's test. And the KMO test evaluates the commonality. Okay, so these are all informations of commonality of your items or of your variables. Okay, if you add them up and get the sum, that is overall MSA. So 0.87. So overall commonality is a 0.87. So we want this commonality is greater than at least 0.7 or 0.8, right? So if this value is between 0.8 and 1, that indicates that this data is good to proceed factor analysis. So we have enough inter-item we have enough intercorrelations, and also we have enough the commonalities. Okay, so let's move on to our fact analysis. So let's check the eigenvalue first. Okay, so this is our correlation matrix, and then eigenvalue. I run it, and then I save the results here. Run it. Okay, this is our eigenvalue, right? So first eigenvalue is 4.78. Second eigenvalue is 3.33. And third eigenvalue is 0.916. Based on these eigenvalues, you can get some idea. You can get an idea how many factors will be needed. All right. So how many factors will be needed based on these results? What do you think? Any idea?
We can extract 2 factors.
Yeah, maybe 2 factors, right? Because the first eigenvalue is greater than 1, is much greater than 1. Second eigenvalue is much greater than 1. The third eigenvalue is less than 1, right? So maybe, and then also how many variables we have? 1, 2, 3, 4, 5. We have 12, right? Okay, so what will be the total variance? We have 12 variable. What will be the total variance?
12.
12, yes. We have 12 variants at variable. Each variable will have one eigenvalue. The variance of the eigenvector will be 1. So the total will be 12, right? So if you get it, okay, this is proportion. So 30, almost the first factor explains 40%. Maybe second factor explains about the 28%. And third factor maybe explains 8% or 7.6%. Okay. So this is kind of a preliminary analysis to get a sense of the number of predictors, a number of factors. Okay. And then you can also plot it, right? So this is scree plot based on the eigenvalues. Okay. So maybe from the first factor to the second factor, it dropped. And to third factor, it dropped a lot. But, but third factor eigenvalue is less than 1 eigenvalue, right? So the contribution of third factor may be the minimal. So we may want to keep 2-factor solution in this case, right? So, but I will run 4 different models here. Okay, this is the EFA. So we use FA function, and then R. This is for data. You have to put your data. You can put correlation matrix, covariance matrix, or raw data. Okay, in our case, our data is raw data. And number of factor, you can specify the number of factor. So, okay, I will try 1-factor solution, and covar equals false. So that means we are not going to use covariance matrix. So that means we're gonna use a correlation matrix. Okay, and then rotate. So we will use oblimin. And this is factor method. The PA is principal axis factoring. Okay. So if you look at the FA, this is FA factor. You can see a lot of options here. R is correlation, covariance, or raw data matrix. Number of factor, number of observations, the rotate method. You can see many different rotate methods right here, right? And number of iteration, residuals, scores, and there are a lot of information. So please review this help session, okay? And then Now we will run the first one-factor solution, two-factor solution, and three-factor solution, and four-factor solution. Okay, I put the one-factor, two-factor, three-factor, and four-factor. And then I will only get loadings, okay? If you put $ and loadings, it will return the only loading information. So here is a loading. These are loadings. And this is loading. Oops, what happened? Loading. Okay, so I just printed 4 different loading metrics of 4 solutions. Okay, so and then go back to my slide. Okay, let's look at the first. This is one factor solution. Okay, so these are all the factor loading. Okay, we want these factor loading is greater than 0.4, less 0.4. Okay, if this factor loading is very low, that means that variable is not related to that factor. Okay, but if you look at this, so item first variable is the 0.25, low, low, right? We can see many low loadings, right? So maybe one factor solution may not be ideal. And then also this is a 2-factor. Okay, this is factor 1 and factor 2. So look at this. This is the loading, factor loading on the second factor, the 0.733, right? So this variable is highly loaded on the second factor. It's much larger than the first factor loading. Right? What about this? Second variable is load on the second factor. The third variable load on the first factor. And the fourth variable load on the first factor. And the fifth is right here. Like you can see a very clear patterns of a factor loading here, right? So what if you have 0.5 and 0.5? What does it mean? A13 is 0.5 and 0.5. How can we interpret it?
It's a multi-dimensional item. It's blended, so it's like cross-loading.
Yeah, this is cross-loading. Cross-loading variables, right? Because this item or this variable loads on the factor 1 and factor 2 equally, right? So we are not sure this item measures the factor 1 or factor 2. So this is a bad case, okay? So this is 2-factor solution and 3-factor solution. This is 3-factor solution. We still see some patterns right here. And 0.4, 0.61, 0.7, 0.9, and 0.8, 0.8, 0.8, 0.8, and 0.8, okay? We see some clear patterns for 3-factor and a 4-factor too. But based on the eigenvalue or the total variance, you need to decide, okay? Do you want to go with the 3-factor solution or 4-factor solution or 2-factor solution? Okay. So in this case, I would say, okay, I'm going to go the 2-factor because based on the eigenvalues, the 3rd factor eigenvalue was less than 1.0. Okay. But if you want to add the 3-factor solution, I think that's fine because 2-factor explains the 61.4% of the total variance. But if you add one more factor, it's the 4% improve, right? But is it worth to add the 3rd factor to get 4 more %? So I will just keep two-factor solution here. Okay. So, and here, SS loading, this is eigenvalue. Okay. So eigenvalue, first factor loading, eigenvalue 4.25, and second eigenvalue 3.11. Okay. This is a proportion of a variance. So first factor, one factor explains the 35.5% of the total variance. And second factor explains 25.9%. And then this is cumulative percent. Okay, so the two factor explains 61.4%. So look at this. This is eigenvalue, right? So this is eigenvalue. This value is different than our, where is it? Where is our again? Eigenvalue. Okay. So when we looked at our eigenvalue from the correlation matrix, that was a 4.78, right? But here, eigenvalue was a 4.26. So why they are different? Any idea here?
Because you have different number of eigenvalues here. We have
Yeah.
12 eigenvalues in the R output, but we only have 2 here.
No, that's not the right answer.
I think the EFA took out the specific variances when it comes out with eigenvalues.
Exactly, right. So, you know, when I just compute the eigenvalue from the correlation matrix, this is correlation matrix, right? So our diagonal is 1, right? So in that case, our eigenvalue looks like this. But when we run EFA, right? So we only use communality part. So our eigenvalue is less than the original, the eigenvalue of the correlation matrix. Does that make sense? If this makes sense to you, do you understand the logic? Okay. All right. And then now, okay, so we got the and then I will get the eigen script plot from the second factor solution. This is a script plot for the second factor solution. And then I want to compare the factor rotation. So I created PA non. This is a principal axis factoring and no rotation, without rotation. Okay. I put here rotation equals none. And then I save it. And then this one, I used limit. Okay. Run it. And then let's look at the loading plot. So don't focus on the coding here. So I will just get the loading plot here. Okay, this is our original loading. Okay. So these items close to the second factor, but these items are close to the first factor 1, right? But this is the factor solution without rotation, before rotation, okay? But after I rotate the using of limit, okay, now we can see much clearer patterns, right? So these items move to the first factor, these are item. The second factor moves to this item. Okay, so the after rotation, so we can get much clearer interpretation of factor loadings. Okay. And then now we can you can also get the factor scores. So this is the factor scores. Okay, factor dot scores and our data set, and this is our model. We already did our model and the method. So this is a factor score method. So we're gonna use a regression method here, and then if I run it, and if you type it, you will see this is a factor score. Oh my gosh. Oh my God. Okay, so this is what? Okay. Give me a second. Let me. Okay, this is the factor scores. Okay. Yeah, I should put this one. So this is the factor 1 and factor 2. The first observation, his score on the first factor is a 0.65. And his second factor score is a 0.73. Okay, what about the third observation? He has a very low level of first factor latent variable, right? But sixth observation, he has a pretty high latent variable on first factor. Okay, what about fourth? He has a low level on the second factor, right? So interpretation is the same as in the PCA. In PCA analysis, you got the PCA scores, right? You can interpret it in the same way. Let me use 5 more minutes, okay? And then you can also plot it. So using this one. Okay, so this, I just plot the factor scores, factor 1 and factor 2. As you can see, mean is 0, right? Average is 0. It's a -4 to 4, -4 to 4, right? So it can be interpreted as a z-score, okay? And then you can add the number, case number. So like, okay, maybe 52. Look at the 52, observation 52. His factor 1 score is very low, right? And his factor 2 score is also very low, right? So this will be negative 3 point something comma negative 3 or something like that. What about 54? His factor 1 score is positive. Maybe it will be 1, but his factor 2 score will be very low, right? And now, okay, so this is a factor score. These are all factor score information, right? These are factor score. And then this factor score is not data frame. So I will transform these factor scores as the data frame. And then I save it as F1, F score 1. So now it is data frame. Okay. And then we can reorder. Okay. I'm gonna order the first factor scores by decreasing order. Okay. So and then run it. Oops, what happened? So this is the factor 1. Okay, who is the highest scores on the factor 1? Okay, 179. Okay, who is the next highest? Second highest, 257. Okay, you can do the same thing for the factor 2. Okay, So this data frame, and then I'm going to order this variable by descending. Okay, and run it and head. Okay, now we will get second factor score. The highest is the 1.41. Okay, and then let's say you want screen some people based on these factor scores. Okay, out of 12 items that you extracted 12 items into 2 factors, and you're going to use 2 factor scores for the further analysis. Okay, so okay, I want to select only some people having PA greater than 1 and P2 greater than 1. Okay, so first factor score is greater than 1, and second factor score is the greater than 1. And then who is that? So which function? I'm going to get index. Okay, these peoples satisfies this condition. 6th, 7th, 14th, 7th, 17th, 44th, okay? And then I'm going to use this index in my row column. So, and then if I run it, oops. Okay, these are the information, okay? So 6th observation, he has the greater than PA, greater than 1 for the PA and P2 scores. We can select these peoples, okay? So in our graph, we had some 54, right? So 54. If you want to look at these 54, you can type column 54 here. If you run it, okay, this is his score. His score was negative 3.77 and a 0.95. So right here. So negative, so 0.5, positive 0.5, and negative 3.77. Okay. Any questions? No questions? Okay, I will talk about the homework. Pushing, are you okay? All right. All right, so you have a data set. That data set is jobapplicants.csv. Okay, that data set includes 15 criteria. Okay, so first criteria is the form of their letter of application, their appearance, the academic ability, likability, self-confidence, lucidity, honesty, salesmanship, and blah, 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 okay? So you have a 15 outcome variable, download it. And then the part 1 is about the PCA. Okay, you have a 15 outcome variable, and then you have to reduce the dimensionality using the PCA analysis. Okay, so the question 1 discuss the positive and negative aspect of using covariance matrix, PCA, rather than the correlation matrix. And the part 2, determine the number of PCs, okay, when using correlation matrix. And C, and interpret your PCs, okay? And then evaluate your PC scores. So what do you think about the applicants of 40 and 42? Okay, and then suppose the late, you already developed the PC principal component equations, okay? And then late applicant submit his application after PCA has been completed, he got 10, all 15 original variables. So what is his PCA scores? Okay, and this is for part 1. And part 2, and using the same data set, the run factor analysis. Okay, evaluate the correlation matrix, determine the number of common factors, and using upper limit and ML estimation, state your factor models. Okay, evaluate the factor loading and commonalities for predictors, and examine the common factor scores and interpret. Okay, and what do you think about the 40 and 42 applicants? And then if the goal of the, if the overall goal is to find the best individuals to hire based on the first two factors, using the first two factors, okay, who are the best applicants? Okay. And then last one is write up 10 points to describe your jurors. Okay. This is assignment 2, and this is total is 100 points. Okay. So if you guys have any question, if you need help, feel free to contact me. Okay. I'm here to help. So any question? It looks hard. Yeah, you should use your brain. Yeah. Okay. All right. If you don't have a question, you don't have any questions? Again, if you have any question, yeah, if you have if you have any question, email me, or I can set up an individual meeting. Okay, I can help. Don't be frustrated. All right, I will see you on Thursday. Okay, see you. Bye.